Okay, students, let's get going. Have your clickers ready. We're actually going to do some non-astronomy clicking right here at the beginning of class concerning exams and stuff. So let me comment on the exams that we took Tuesday. The grades are up in web courses, and go ahead to 50% light. Okay, good. So it looks like this. Let me make this a little bit bigger for you. So the way it breaks down, you can see here, this is just a screen grab from sample student. The Scantron score is here on your grades page, and that's based on possible 44 points. And then below that is the exam 1 clicking score, and that's based on a possible 6 points. Now this example, the student got 40 Scantron points and 1 iClicker point. And so up here, the exam 1 total puts both of those numbers together. Okay, so for this example, that's 41, and it's out of a possible 50. Now, let me pause here for just a second to let you know that occasionally I'll put 1 or 2 bonus questions on the exam. All right? And so the exam scores, I mean, if you ace everything, it might add up to 53. All right? And you may think, well, does that change the grading? Well, it changes your grade if you get 53 out of 50, but it doesn't change the denominator. So you always want to think, you know, I'm getting 53 out of a possible 50, or whatever your score is out of a possible 50 on a midterm. That 50, the notional basis for that grade does not change. Anything that you get bonus-wise goes into the numerator, but not in the denominator. So the denominator stays at 50. For the final exam, if I put 5 bonus point items on there somewhere, it would still be a 100-point final that you could get 105 points on, which is nice. All right, so just so you know, and bonus points do not disappear. All right, and so if you get some bonus points, just think of them as being tacked onto your final exam. Everybody's going to be here for the final exam. So if you have, you know, and nobody, some of you might miss exam, or might have missed exam 1. Some of you might miss exam 2 or exam 3. Everybody's going to be here for the final. So just think of it as pointage that's attached to your final. That's another way that you can think about bonus points. Speaking of bonus points, the observatory bonus points. Now, I know everybody's wondering about bonus points from the observatory. Raise your hand if you went last night. Nice. We're going to have an iClicker question here in just a second about that. They will go up in web courses as soon as the UCF Astronomical Society, those guys that run the sessions, as soon as they get the handouts to me. And they've got students from all different sections, you know, not just this one. So they have to sort them out, and then they get them to me. So next week, let's see, today's Thursday. So I'll probably see a stack in my mailbox of your handouts next week in my faculty mailbox, maybe the week after. Sometimes they're kind of slow. And it will be 8 bonus points. And if you didn't make it last night and you would like to, there's a possibility that February 22nd will be your next opportunity. It depends on the weather. Okay, everything depends on the weather. All right. So far, we got a good one last night. You know, I was home. I was out and about last night, so I didn't get home until after 9, and you know, I got out of my car and I saw how bright the moon was and how clear the sky. Did you guys see Orion last night? Clear as a bell, and the moon was so bright you could read a newspaper just about. I mean, that as far as I'm concerned, in my opinion. So all this stuff depends on the weather. And here's one more thing that is nice. If you go again, you get another 8 bonus points. So now here's what it looks like in your grades page. It'll be right in here. Now, right now, I've got a slot for it, but nobody's got any points, so don't worry. The observatory bonus points, sometimes they go on fast if the UCF Astronomical Society moves fast, but sometimes they don't move so fast, and we just got to go at their pace. So, but be patient. That's where they'll show up. All right. Now, any questions about bonus points? Yes, in the front. Okay, if you have a job or something and you cannot make it to any of the observatories, they're all about 7:30, 8 o'clock, and they go for about an hour and a half. You know, you have a little bit of opportunity. But if you know that you can't make them, we have other stuff planned so that you can get 8 bonus points total, but not have to go to the observatory. So everybody will get a shot at least. You know, this might be the only shot for the observatory. No, you know, it might be the rest of the scheduled nights. It might be cloudy. You never know. All right. But there'll be an opportunity at the end of the semester. We'll have some review activities that will generate 2 review activities that will generate 4 bonus points. So if you feel like, gee, Dr. B, I can't make it because I have a job and my boss is a real you-know-what, then we got something set up for you. But it'll be at the end of the semester. But if something, you know, if something opens up and you find that you can go, then go. But it all depends on the weather. Now, any other questions about exam scores or bonus pointage? Was that about, okay, question.
Is there a way to find out what we missed on the clicker score question?
No, unfortunately, unless you come and talk to me about it, you know, in office hours and stuff. It used to be, the question was, is there any way to find out what you got wrong on the clicker questions? And unfortunately in Canvas there is not. In the old web courses, which was based on Blackboard, have you ever heard of Blackboard? It's a similar kind of software. We could upload any set of data that we wanted, text or numeric. So I would sometimes, you know that code question we had a couple weeks ago where you formed a sentence? I would sometimes upload your entire sentence so you could see, and the score that it got. And I can upload scores, individual scores for questions, but I can't upload, you know, any text. So, like for instance, this test had that mini code question, 2 symbols, and which is nice to talk about. But unfortunately, I can't upload your symbols the way I. But if you come to office hours, we can look it all up. You know, look it up on the spreadsheet and talk it over. So it's there, but you can't see it through Canvas because Canvas. It's Canvas's way or the highway, unfortunately. Another question. Okay, let me ask a question. Dr. Brickner, is there a way for me to know what questions I got wrong on the Scantron? And the answer to that is yes, there is. We're developing a way to get your printout that we used to get it printed out onto paper, and then the day after the exam, or the lecture after the exam, we would hand it out to, the TA would take half and I'd take half and just call everybody by name and stuff. But now we have it on electronic format, and we're trying to figure out a method to get it to you electronically through web courses as a PDF. So we can't help too much with the clicking data, but we can with the Scantron data. And in addition to that, let me make one additional point. With those exam printouts, I'm going to ask you to take a little quiz as soon as we get it all figured out and stuff, where you answer yes or no, a one-question quiz, and signify whether you want your printout or not. And most people will want it, and hopefully we'll be able to get it to you as a PDF. So otherwise we'll have to print a huge PDF file through the computer and make 270 copies of it, and it'll be a mess. But hopefully we can do it electronically. And one more thing, you may think to yourself, well, Dr. B, I've seen those Scantron printouts. They're nice. They tell you that you got like number 7 wrong, or that number 31 you bubbled in two letters, or what have you. You can see your errors, but it doesn't tell me what that question was about. But I do have a method for telling you to look at your printout and then look at a little blurb sheet about exam form A, B, C, or D, depending on which one you have. And you'll be able to correlate your incorrect answers on the printout with the blurb sheet. There'll be a little it won't be verbatim, but it'll give you the basic idea for each of the questions on the test. So we'll try to get those ready for you as well, the blurb sheets. You'll see, as soon as I post them, there'll be a little page with blurb sheets and stuff. And those will be nice because you can then use the blurb sheet and your exam printout as kind of a little mini study guide, especially if you're trying to study for the final and identify the basic areas that you got wrong in exam 1, 2, or 3, and if you don't want to repeat those errors, study those things a little extra hard. Okay, so that's that. So we're trying to get this squared away. This is the first semester that we're trying this electronic version, so hopefully it'll work good. Now I have some iClicker questions about the observatory. So turn on your iClicker, and I have 2 questions. And they're going to be short answer type questions. Go ahead and start it. And so I'm going to mark your answer correct whichever way you answer. So just answer truthfully. Did you go to the observatory last night? I just want to count, that's all. If you type yes, good. If you type, you'll get correct for both of those. So. All right. Don't type the word no. Type in the letter B. For this one, you can use the B, but use the B button, but you have to hit the send button as well. Go ahead and mark that one. Oh, sorry, they selected it. No, you have to just type a letter. A letter's fine. And so, but hit the send key, right? Because you're in short answer mode. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, and it looks like we had 41 people went and 144 no. So that's about 2/7, about 28%. That's pretty good. No, 2/9, about 22%. Yeah, 22%. So that's good. Now this next question is also, this one you're gonna, so hit the refresh key and answer this one. This is short answer as well. what did you, for those of you that went there, what was the most interesting? Just type it out in a few symbols, a few letters. And if you didn't go, just say, next time, Dr. B. Listen to that clicking. Nice. Yeah, I'm just curious about B. Who typed B? NTDB. No. Oh, I'm not really getting through to you guys. What is that? Oh.
I think it's supposed to be moved.
Yeah. Oh, that's interesting. Yeah, we're just grading everything correct as we see it appear here. So they changed it. Next time, Dr. B. It sounds like a movie, you know. You know, when Dr. Evil gets foiled. Next time, Austin Power. Next time. What was Chuck Norris's name in? Oh, Walker. Walker, Texas Ranger. Next time, Walker. Next time. Good. Boy, it's a good thing I'm not grading for spelling here. Oh, Lord. Okay. This is... That's good. No, that's good. That's good. Even considering the spelling difficulties. It's all right. We're not trying to be too fussy here. All right, 20 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, stop it. Switch over to computer display. Let's take a look at the answers. So this is good. Andromeda Galaxy, all the telescopes. Next time, Dr. B. Dr. C? What? Next time, bro? Don't tase me, bro. Mr. B? No, that's Dr. B. That one I should grade wrong. And we'll grade all these rounds. Net moon, life. I didn't go. Full moon. ET cluster. What is... Owl cluster? Yeah. The big moo? Somebody typed that, but then they changed their mind. Andromeda. That's good. So, anyways, we'll try to do a similar little survey when you guys, when we do it again, hopefully February 22nd. All right, and go ahead and grade all those things correct while you're at it, and I'll continue with lecture here. All right, now we're going to go back to astronomy, and we're going to talk about the moon for the first main part of lecture. We're going to be focusing on, for the next two lectures, the terrestrial planets and the moon. And you may think to yourself, Dr. B, the moons are not planets. But actually, the origin of the moon is related. It's almost as if the moon could have been another planet. And to talk about that, we're also going to talk about oxygen isotopes. All right? Now, if you haven't heard that word before, oxygen isotopes, let's go over it. Every element on the periodic table has a unique number of protons in its nucleus, and if it's a neutral atom, it will have the same number of electrons in its orbit. You know, I have to change something here. Let me pause this. And these are hydrogen isotopes. Okay, so if it's neutral, there's the same number of electrons in orbit as there are protons. And it's the electrons that control chemical reactions. All right? What the electrons do nicely and easily, what they refuse to do, that's what, and then, you know, with a different atom, you know, like hydrogen and oxygen, you know, the electrons are different. They have different properties, but they make water, H2O. Many elements, however, come in nuclear variations, and those are called isotopes. So it's important to remember this. So there's a set number of protons, but in the nucleus there's variations in the number of neutrons, and this is naturally occurring. So here are 3 pictures of hydrogen isotopes. One of them, the first one in the upper left, is just regular hydrogen, a proton and an electron in orbit. The second one in the yellow figure, that's called deuterium, D-E, I'll spell that for you, I don't have it on the slide. It's D-E-U-T-E-R-I-U-M. And it's also called double heavy hydrogen. It's, chemically speaking, it's hydrogen, but its weight is basically double. Most of the weight of an atom is in its neutrons and protons. Electrons are pretty shrimpy, so they don't really add much. You know, add an electron, subtract an electron, doesn't change the weight a whole lot, but add a proton or a neutron, subtract a proton or a neutron, it changes the weight of the element quite a bit. All right. And it also affects the nuclear reactions. All right. Now we're going to do iron here in a second, but I want to finish up by looking at this orangey one at the bottom. Now that one has 1 proton, the red circle with the letter P, and this one has 2 neutrons in it. So in the nucleus there are 3 nuclear particles, or what we call nucleons. Let me spell that vocabulary word for you. N-U-C-L-E-O-N, nucleon. So 3 nucleons, and this one is called, for that reason, it is called tritium, T-R-I-T-I-U-M. The first isotope is deuterium, and the next isotope is tritium, T-R-I-T-I-U-M. T-R-I meaning 3. There's 3 nucleons. Now, chemically speaking, these hydrogen variations, they'll all behave chemically the way regular hydrogen does. They're just a little heavier. And you may say to yourself, Dr. B, is this related to this topic I sometimes hear in the newspapers, heavy water? The answer to that is yes. Heavy water is a water molecule with usually a regular hydrogen and a deuterium. So it would be DHO. Deuterium, hydrogen, and 1 oxygen instead of H2O. But chemically speaking, they're the same. And heavy water, DHO, is abundant enough on our planet. You know, we can count it. You can filter it out. You know, you can count up, you know, how many grams of DHO that you get and how many grams of water you get. I mean, for every ton of water, you get a few grams of DHO, heavy water. But you can measure. But chemically speaking, you know, it freezes. Actually, I shouldn't say that. Freezing, it might be a little bit different. But it'll bond with things, you know, like carbohydrates and stuff, just the same way. And raise your hand if you have a water bottle with you today. Hydration. Bunch of yous. Everybody that just raised your hand, you're carrying some deuterium in your water bottle, in your hydration reserve. It's just, you know, this is the numbers. In World War II, there was this famous program in Norway where they were prior to World War II, they had, some of the chemists and physicists had isolated water at this big hydroelectric dam for the Norwegian Power Company, you know, up, I forget the name of the town, up in the mountains in Norway, and they had separated a lot of heavy water. At the outbreak of World War II, the Germans invaded Norway specifically to get that heavy water so they could build an atom bomb. Now, they never succeeded. They didn't even get close, we now know. But everybody was nervous. All the Americans and the English were very, very nervous about it, because everybody knew about it. You know, they'd published papers and stuff, and, you know, so everybody knew about the heavy water supply up there in Norway. Nobody else was doing it. Nobody thought it was that important until World War II. But anyways, they had this big supply of it up there, and they didn't want the Germans to get a hold of it. So I think they smuggled out most of it at the early stages of the war over to Britain. But then the Germans invaded, and they started making, you know, and they just basically filtered it out of the water, you know, various filtering methods. And so the Germans had it cooking. They were getting their heavy water, and so the British and the Americans and the Allies decided to, you know, bomb the you-know-what out of that power plant. And I think they did succeed in it, and the Germans rebuilt it and stuff. Anyways, it's called the Heavy Water War. It's a separate little war up there in Norway about heavy water. And it's this DHO, the second one here, deuterium. Tritium is something that's harder to find. Tritium is radioactive, and it will decay, I believe it will decay in a short amount of time. We can make it in a nuclear reactor. It's one of the most valuable substances on the Earth, and regular civilians are not allowed to have any tritium. It's a control, it's like uranium. And the reason for that is tritium is an element, and deuterium as well, that they could use for making a hydrogen bomb, you know, a thermonuclear explosive. And they take these two variations of hydrogen, and they can use regular hydrogen as well. But tritium and deuterium are particularly easy, significantly easier to get to fuse into a fusion reaction, and that's what they do for nuclear weapons. So normal civilians are not allowed to have, although they do use deuterium, or they use tritium, I've read, to make paint that glows in the dark. You know, for like guns, you know, for people that are hunting at night, gun sights and stuff like that. So anyways, let's talk about iron. Iron, every element, I think every element has an isotope variation. Hydrogen has 3. Iron isotopes, they all have 26. That's the atomic number for iron. Symbol is Fe. And here's the most common isotope. Now write that down carefully. The superscript upstairs before the chemical symbol Fe, that's 56. All right, so we call this variation iron 56. Now the number in the downstairs, the subscript before the chemical symbol Fe, that's the atomic number. All right? And that tells you how many protons are in the nucleus. Now 56 tells you how many nuclear particles total are in the nucleus. All right? 56 nucleons so that's like its atomic weight, because most of the weight is in nucleons. So what this symbol says is that you have 26 protons and 56 total, so that means you've got 30 neutrons in the nucleus. And for this flavor of iron, right? And this is about 92% of all the naturally occurring iron on our planet. Okay? If you go to some other planet, some other star system, you might have different abundances, but here on good old terra firma, it's about 92%. Now here's another isotope, iron 57. All right. Now this one is similar, 26 protons in the nucleus. If it's iron, it's got 26 protons. Done. That is what, and the 26 electrons, that is what gives it its chemical identity, its position on the periodic table. But 57 tells you about the nucleus, and so 57 nucleons, and this is about 2% of all the iron that we find here on Earth, is iron 57. So most of it's iron 56, very abundant, but there's a little bit of iron 57. And I want you to think, how many neutrons does that mean in the nucleus? 31, that's right, 31. All right. Iron 58, here's another, there's 4 isotopes, 4 stable isotopes of iron. Iron 58, 26 protons, 32 neutrons, and that's about 0.3% of the iron abundance. So this is like, separating the isotopes. What they'd have to do with iron is they'd have to vaporize it, like totally melt it and then totally vaporize it at an even higher temperature and then separate it as a gas, which you got to have pretty hot kitchen for that. Anyways, about 0.3% terrestrial abundance on that. Now, I'm going to list out, go ahead and write down iron 54, 26. That's about 6%, but I'm going to ask you an iClicker question about this. Now, this one's going to be a multiple choice question. So hit the refresh key. And let's start with the basics. How many protons in this baby? And there's your full isotopic notation. So go ahead and vote for that. 20 seconds to vote. Ten seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Hold it. Come on, you guys, make a vote. All right, click. Yeah, most of you guys got that, 91%. Yeah, 26. That's what that lower number tells you. And the periodic table, it starts with hydrogen up in the upper left and helium at the upper right. And helium is element number 2, so it has 2 protons in its nucleus. And then you go down to the next level, and lithium is right below hydrogen, and that's number 3. There's 3 protons in its nucleus. And the entire periodic table is arranged in that way. All right, iron 54, how many neutrons? If it please the court. All right. And believe it or not, iron 56 and the iron isotopes are actually pretty important to the theory of black holes. So actually, these isotopes, we're going to be talking about them between now and the end of the semester, here and there. So it's good to get familiar with them. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, you guys are geniuses. Most of you got that one right too. All right. So good. Just keep that in mind. It's a good couple, 3 examples. Iron 50. And calcium, neon, most elements. I think every element. I'd have to look it up. I'm not an expert on the periodic table, but I think most elements have isotopic variations. And by the way, side note, other isotopes are unstable. And that means that they decay, the nucleus decays. All right, but the different isotopes are important in nuclear reactions. You know, like in a nuclear reactor, which uses uranium and plutonium, which are they're stable, but they're easy to break apart. You know, nuclear fission, fission. But the isotopes are pretty important, and we're going to be using them to study the moon. So let's talk about the impact formation of our moon. The best theory, I don't know, do you think it's the best theory? Impact formation for the moon?
Yeah, it's
I
pretty
mean, that's what you study, right?
Yeah.
Impacts.
makes sense.
The current theory, I mean, there's all kinds of theories. You know, the moon is made of green cheese and stuff. I guess that's a theory from back in the olden days. But we think that the moon is different from the other moons in the solar system. You know, like the moons of Jupiter, the moons of Saturn, even the moons of Mars. We think those are captured asteroids. The moon, we think, formed as a product of a collision of Earth with another Mars-sized planet, we think, about the size of Mars. And it's been nicknamed Theia, Theia. And so we've done computer simulations, of banging two big planetary things together of certain sizes. And do you do things on that scale, or do you do asteroid size versus Earth?
Size.
Okay, so Jenny does asteroids, which are not as big as a planet, but other people do, simulate this level, planet to planet. So this is like a Mars crashing into an Earth. And you get all kinds of smithereens everywhere, and they all go into orbit. And some of them, leave and they never show up again. So you lose a little bit of mass. And some of it goes into orbit. Some of it gets sucked back down into the Earth, and eventually a moon forms. Now, the interesting thing is they've been studying the isotopes of oxygen in terrestrial rocks and moon rocks. And they have found that the oxygen 18 and oxygen 17 abundances, that's two isotopes, stable isotopes. By the way, the third stable isotope of oxygen is oxygen 16, and that's the one that's like 97% of all the oxygen, or 98% of all the oxygen. And these other two, oxygen 18 and oxygen 17, are fairly rare, a few parts per million. All right. So, but anyways, moon rocks and terrestrial rocks, we now have measured them really carefully and found that the isotope ratios are fairly the same. And therefore, we think that in this impact, there was a lot of mixing. In other words, I probably shouldn't say homogenized, but the mantle of the Earth and the mantle of this impactor, Theia, the smithereens and the debris mixed fairly thoroughly, we think. Question?
You mentioned that oxygen 16 is 90% of oxygen, right?
90-something%. You could look it up. Yeah, it's most oxygen. I don't know, it might even be 99 point something. Yeah.
So couldn't it just be that's just how abundant the oxygen isotopes are?
So here's the question. Doesn't that just mean that all the planets have the same oxygen abundance and of the isotopes, the same ratios? And the answer to that is yes, that is a possibility. However, Mars does not have, and we've studied rocks from Mars. Matter of fact, we've got some asteroids from Mars that have been blasted off. An asteroid impacts Mars and sends fragments flying, and some of them land on Earth as meteorites, and we've bagged those. We've got them. And we know that the oxygen ratios are not the same for Mars. the isotope ratios. So Jenny's over here saying, yep. Dr. B, you got it. So the answer to that is no, it's not true. All right, and that's one of the deluxe questions. All right, if the moon now has about the same as Earth, what did Thea have to have coming in at a certain angle, a certain energy, and with certain amount of mixing and turbulence and stuff in the collision to get to the fact that today that the moon and the Earth are the same. So we're still trying to figure out what Thea had. We think that Thea might have been different, but since the moon and the Earth are the same ratios, the same abundances, if Thea I'll put it this way, if Thea was different, then there was a lot of mixing. So that now the leftovers after the collision, the incoming had different abundances. They collided, the debris all mixed together, and now the moon and the Earth, look like they're pretty much the same. So if Thea was significantly different, then that means there was a lot of mixing, of all the debris and stuff. So we're still working on it. And there's some journal articles. I'm going to show you a couple diagrams. Go ahead and make a note of this. There's a journal article from just 2 years ago, 129/16, so it's pretty recent, and there's a news article in Science. Here's a sketch of it. I'm going to just give you a look at this. This is a plot of over here on the vertical axis is one of the oxygen 17 ratios. And then down here on the bottom is oxygen 18. So different ratios. The one on the bottom is compared to SMOW. So go ahead and make a note of that. We're going to be talking about SMOW quite a bit. SMOW stands for Standard Mean Ocean Water. So the bottom scale, the horizontal scale, is comparing everything else that's on this chart, moon rocks, terrestrial rocks, with the oxygen ratios in water. And rocks are going to have different ratios than water. So water is going to have so many isotopes of oxygen, and terrestrial rocks going to have a slightly different ratio, and it shows up on this chart. And it's similar for the vertical scale. Standard mean ocean water of Earth. So that's the normal standard. So we compare that, we get an asteroid fragment, a meteorite, a moon rock, or anything, and we compare it just to the standard, which is ocean water. And for, let's see, for carbon has isotopes as well. We use a geological formation up in South Carolina, a limestone formation. We compare every carbon-bearing object in the universe to this limestone formation up in South Carolina, right? But if it's oxygen, we compare it to water. And we compare hydrogen ratios to water as well, SMOW. Anyway, the reason I'm showing you this is because this diagram plots up isotope ratios, oxygen 17, oxygen 18, two different axes. And these ones that have a circle with a half moon in it, some of the half moons are facing to the left, some are facing to the right. Those are lunar rocks. And most of those are inside the gray wedge-shaped area. Now, all the white symbols, these ones up here, those are Earth rocks. This one says BC, what does that say? BC olivine. Olivine is a mineral. BC, or SC, I guess it is. That stands for a place on Earth out in Arizona. All these things down here. See that? Mauna Loa, Bushveld, what does that say? Anorthosite. That's down in South Africa. Let's take a look. SC. So go ahead and make a note of this. Yeah, we're comparing moon rocks to this formation in Arizona, the San Carlos volcanic formation. You know, igneous rocks, and the stuff that we've brought back from the moon is, you know, the moon is mostly igneous rock. There's no sedimentary rock in the manner that we have sedimentary rock on Earth, but there's probably metamorphic rock there. But anyways, San Carlos formation. So for certain features of rocks, we compare it to San Carlos. Gore Mountain, there's garnet. Garnet is a gemstone, red gemstone. And the place where, or one famous place where it's been mined is upstate New York in a place called Gore Mountain. And just so you can orient yourself to the map, here's Albany, New York down here in the lower right side. Here's Montreal up here on the upper right. And then down here, that is Buffalo, New York, Buffalo, New York. And then up here is Toronto. All right, so that's the basic area. So upstate New York. And that big blue thing is Lake Ontario. So we're comparing moon rocks. We're comparing the oxygen isotopes in moon rocks to gemstones out of this mountain. It's just one of the geological standards. Mauna Loa out in Hawaii. You know, it's a very active volcano. And a lot of lava flowing out of that, you know, and you know, you don't want to get too close to it. Except, look at that guy. See this guy down here? I don't know. You'd have to have like fireproof feet to get that close. Because those rocks are really hot. It takes a long time for them to cool off. The Bushveld complex in South Africa. Here's a little diagram. You can look it up. It also has diamonds in it. So it's kind of a cool geological formation. So, you know, we compare the oxygen ratios of the isotope ratios to, you know, all kinds of things. And they're all the, you know, it's all the same neighborhood. So we take Apollo moon rocks, and they actually analyzed one lunar meteorite. And they figured, you know, if this is really true, it basically tells us how big Theia was. So they think it's about Mars-sized, and that it had to produce a lot. Even just knowing that it's thoroughly mixed tells you that it couldn't impact, you know, like a direct hit. It had to come in oblique, and at certain energy, certain orbital energy. So it's all this stuff, you know, and here's a quote from chapter 9.4, The Origin of the Moon. All this stuff tells us a lot about the formation of the moon. So it's really interesting to read about. So here's this pull quote. It says, the moon's raw material is derived from the mantles of Earth and the projectile, i.e. Theia. The absence of metal is easy to understand, and that's for the mantle of Earth. There's a ton of metal in the core of the Earth, but in the mantle it's relatively sparse, same as on the moon. Did you know what the two most abundant elements are in the crust of the Earth? Iron, right? No, not iron. You know what it is? Silicon and oxygen. Most rocks, quartz, sand. You know what the chemical formula for that is? Silicon dioxide. Silicon and oxygen. One silicon, two oxygens. SiO2. Did you know that if you buy powdered, it's probably not true anymore, but if you look at the ingredients list of things like detergent and other stuff, you'll sometimes see silicon dioxide. Matter of fact, I think I saw a toothpaste that had silicon dioxide in it. It's sand. They put it in stuff. And so, now they don't put it in liquid detergent, okay? But powdered stuff, they put silicon dioxide in it. Because it's everywhere, and it's it flows, sand, helps things stay powdery and stuff, I guess. I wouldn't want it. Can you imagine? Yeah, let me just take a little bit of sand to brush my teeth with, but that's what they do. Some companies, I guess. Maybe they went out of business, I don't know. Anyway, so the origin of the moon is, it's really, really interesting. You can read about it in chapter 9, which is mostly about the moon. Let's talk about chapter 10 stuff, terrestrial planet concepts. And let's take our first look at the terrestrial planets. So the terrestrial planets are the ones that are like Earth, terrestrial. Okay? So they're extraterrestrial in location, but geologically speaking, they're terrestrial in geological composition. So that's Mercury, Venus, Earth, and Mars. And actually the moon is terrestrial as well. We call it a moon, but it's quite similar to Earth. So so there's the list. And we think that when the sun was forming, it's this big swirling, burling mixture of hydrogen gas, Emily, and interstellar dust, just swirling, like we see out in the universe. Did you guys see the Orion Nebula last night? Okay, the big swirling clouds of gas and dust, and that's where stars are born. And when they form, there's a little bit of spin and a little bit of condensation, gravitational attraction brings things in and solidifies stuff eventually into the sun, into the star, and then frequently into planets orbiting the star. And we think that there's a dividing line around the star, inside of which rocky and metallic inner planets form, because they can withstand the heat in the inner solar system. And because it's close to the sun, right? And the cold part of the solar system is outside of this boundary line. We call it the frost line, although I've heard other terms for it. It basically is it's not like, some hard, ultra precise boundary, but somewhere between Mars and Jupiter, out somewhere and past the asteroid belt, is a line or a location inside of which only stuff like iron and silicon and metals and stuff can resist being evaporated. They'll stay solid, they'll solidify, but something like CO2 ice, dry ice, water ice, ammonia ice, and forget about the gases like hydrogen, atomic hydrogen H2 or molecular hydrogen H2. Those stuff are considered volatile, and in the inner solar system they get vaporized, right? And the pressure of sunlight can actually push those things out past the inner planets. And so the outer planets like Jupiter and Saturn, Uranus, and Neptune, they're much bigger, and they're mostly made of stuff like hydrogen and helium and water and CO2, a lot more water and CO2 and ammonia and stuff in the outer planets. Hydrogen, helium, and hydrogen-bearing compounds. So methane, CH4, carbon and 4 hydrogens. Ammonia, nitrogen, NH3, nitrogen and 3 hydrogens. Okay, that's more. It's not very abundant here on Earth. When we can make them in a lab or in a factory, ammonia making factory, but there's not like, deposits of ammonia on the Earth. There's deposits of iron ore out the wazoo. There's even lots of diamonds on Earth compared to other places. But the outer planets, which we'll study next week, are made from different compounds. So this is, like I said, somewhere between the orbit of Mars. Orbit of Mars is 1.52 astronomical units, and Jupiter's about 5.2 astronomical units out. So somewhere in there is the, it's not like something's forbidden to be an ice inside the frost line, because comets are made of icy materials. Asteroids are made of rocky and metallic materials for the most part. But comets come to the inner solar system all the time. We can see them from Earth. And the fact that we see them from Earth, they make this brilliant glowing tail that catches the sunlight and glows even in the night. That's all from ices like ammonia ice, carbon dioxide ice, water ice, that gets vaporized when it gets close to the sun. So when those comets get inside of Mars's orbit, inside Earth's orbit, they're going to start to outgas, and we're going to start to see that comet tail. And it's all because of this. All right, basic specs for Mars. Let's just trot through some of these. And unfortunately, I don't have the planetary fact sheet, but if you type in planetary facts and NASA in Google, you'll come up with a really nifty planetary fact sheet for all the planets. It's really nice. Just like their radius, their eccentricity, the orbital period, and orbital speed, all the physical features. So it's further from Earth, 1.52. It has a longer year. It's colder. It's not that cold. On a warm summer day in the equator of Mars, you could walk around, like maybe the way you're dressed today. It might be 40 degrees Fahrenheit. Okay, so you'd have to bundle up a little bit. But you'd also need like scuba tanks because it doesn't have much oxygen in the atmosphere. Spin rate, 24.6597 hours per day. So the Martian day is a little bit longer than Earth, not too much. Its axis of rotation is tilted a little bit askew compared to Earth's axis. And the sun's sun's rotation is rotating down there in the center of the solar system, and the sun is rotating, and its rotation axis points toward the North Star as well, or points in that direction, but not exactly. Earth's points exactly to the North Star. And Mars, it's 1.85 degrees away. So if we were on Mars, we would see the North Star kind of making a little teeny circle. It'd still be useful as a navigational, eyeball navigation guide, because it doesn't really move a whole lot. But here on Earth, it doesn't move very much at all. It's very, very set. As we know from talking about Kepler, the orbit is fairly eccentric, so it's significantly closer to the sun during the southern hemisphere summer. And for that reason, it has more extreme seasons in its southern hemisphere. And we know that when Earth changes twice a year from winter to summer and back, that day is called the equinox, the vernal equinox in March 21st, the autumnal equinox at about September 21st. Those tend to be times when there are drastic storms, stormy weather on Earth. The same thing, but it's extreme in Mars. Here's a kind of a cool image. Look at this. All right, this is 2001. June 26th, before the dust storm. And just a few weeks later, September 4th, so that's like 2 months later, 2 point something months later, look at that. That is a dust storm that basically covers the entire planet. So make a note of that. Martian weather can be global. Very drastic changes. This is the first picture here on the left, June 26th. That's like Mars having a fairly clear day. You can see the ice caps, and you can see the plains, and you can see the Valley Marineris, this big kind of, let me get my cursor over there. There we go. This kind of big sideways gash that in the olden days, like 100 years ago, when they were, 100 and something years ago, the late 1800s even, they thought those were canals. They thought, that the Martians had built canals to irrigate, Mars. And that's a whole other story, the canals of Mars. But that famous, if you've ever seen that movie, The War of the Worlds, there's the version from the 1950s, I guess. And then there's a version with Tom Cruise from a few years ago. And they're both really scary. So don't watch them at night because, it's okay to watch scary movies, but not in the middle of the night. Anyways, those two, they were based on a novel written by H.G. Wells. I think he wrote it before World War I. But they thought in those days that there were intelligent life forms on Mars. They thought that thing was a canal, and there were guys building the canal, there were guys, farmers, and using the water. Like what we do here on Earth. We dam up rivers for hydroelectric power. The water builds up behind the dam, and we use that water to irrigate the desert, like out in Washington State, the Inland Empire, Columbia Plateau. It's amazing. Israel, they do the same thing down there, over there in Israel. All over the place we do that. But yeah, H.G. Wells and those guys in that era, so 100 years ago and more, they were thinking about that as a... But if you look at it, it's astounding, the change. You could just barely see, I don't know if you guys can see it, you'll be able to see it on YouTube, but you can just barely see, that Valley Marineris, that's what this gash is. It was discovered by the Mariner spacecraft. I think that's why it has that name. You can read about it in chapter 10. Astronomical unit for Mars, or the distance, about 757 light seconds. Yeah, that's about 1.5 times. Earth is about 500, so 1.5 of that is 750. So Mars comes in a little bit above that, 757 light seconds. Yeah, so that's about as far as the sun is from Mars. Some more basic specs. To walk around the equator is a lot easier. It's smaller than Earth. It's about 13,000 miles. Earth is about 24,000 miles, so it's a little bit smaller. So we think about it, Earth as being the same size as Mars. Venus is close to the same size as Earth, but Mars is smaller. We have various spacecraft up there right now. We have a couple rovers, I think, we have several devices down on the surface, including a few that have crash landed on the surface. And we have some in orbit. And one of them on orbit, the Mars Express, is specifically designed to map things underneath the surface with what we call ground penetrating radar. And it's been able to discover buku water frozen under the surface layers of the Martian ground, the soil. So it's just, if you look at the map of what Mars Express has found, it's everywhere, my friend. There's water, there's tons of water, literally tons. We have this ground penetrating radar. So if you have a radar on a spacecraft aimed at Earth, and if your radar has the right frequency and enough power, then it can map stuff underground in certain rock formations. And there's an interesting story about this. Back in the 1960s, the Soviet Union and the United States were negotiating this nuclear test ban treaty. And so to ban atmospheric testing of nuclear weapons, because it's really bad. So they were negotiating this treaty, and they wanted to be able to verify that the Ruskies were playing fair, that they were, you know, we had an agreement, or we were negotiating an agreement, and we wanted to be sure that they were honest about it. So they put this spacecraft up with ground penetrating radar. And it was top secret. But they still wanted the Ruskies to know that we had it. So they didn't try to, you know. So what they did was they had this spacecraft, right, and it's got this ground penetrating radar. And what they did was they published a study in National Geographic of subsurface canals in the Nile Delta. And so you could see all these structures in the Nile Delta that were buried by, you know, feet of sand, but we could see them with our radar, our ground penetrating radar. So you're reading National Geographic. Oh, cool! Look at this stuff that they found from space. You know, all these channels of the old, you know, the Nile Delta. You know, it used to flow here, and now it's covered up, and it flows over here now. So you're everybody's, oh, cool, pictures from space, even underground pictures, except for the Russians. When they read that issue of the National Geographic, they went, oh my God, they got everything. They got all of our underground stuff. They could see everything that the Russians were doing. And the Americans wanted the Russians to know, don't try anything, we got it. We got our eyes on you. What do you think the Hubble Space Telescope is? My God. Anyway. So as much as 1/3 of the total carbon dioxide of the Martian atmosphere is actually in the polar ice caps, and it doesn't melt. You know, carbon dioxide doesn't melt. It goes directly from solid ice to gaseous carbon dioxide. It's called sublimation. And then it mixes in the atmosphere, and it gets redeposited in the other polar cap because it's cold down there. And then 6 months or half a Martian year later, it reverses the process. And so Curiosity, the rover, we've talked about it before. It's also looking for methane, CH4, and other organic compounds. And there's a lot of stuff we're looking at. Now, I'm just going to show you one more slide. On Tuesday next week, we'll start talking about volcanoes, Earth, Venus, and Mars. There's a picture of one on Mars, about the size of Arizona. So your homework this weekend, read about volcanoes in the OpenStax textbook, and I'll see you on Tuesday. You're dismissed. 1:15 on the dot. There's my cursor. Come on, baby.